Hello, everyone. I am Anisleidy, and I am Pedro's PhD student, and I'm going to introduce our work on high-dimensional neural mass models with distributed delays. An important tool at this moment in neuroscience is the construction of mesoscopic neural mass models, which describe neuronal dynamics over time by means of stochastic or random differential equations. Neural mass models are used to simulate electrical activity of the brain, understanding the architecture of neurons. One of the classical neural mass models is the one formulated by Jansen and Reed, which study the dynamics of three neuron masses, two excitatory and one inhibitory. Our new approach in this model is the introduction of a connectivity tensor, including temporal dimensions with arbitrary delay instead of using a connectivity matrix. Our numerical integration methodology is based on two crucial steps. First, we solve the system of equations with a sufficiently small integration step to ensure that input to each neural mass from other masses can be calculated before solving the neural mass equation. This approach uncouples the integration of each neural mass with significant simplifications in the solution of the system of differential equations, which are now low-dimensional. The second one is finding the inputs for each neural mass, which is a combination of time shift versions from other neural masses outputs and the connectivity strength. This information is included into the Connectome Tensor. Traditional methods used in this field to integrate numerically are based on Euler-Maruyama, Helm, and Runge-Kutta schemes. Those methods don't preserve the original dynamics of the continuous systems, and the standard solutions become calculations frequently explosive. A solution to these problems was introduced by Ozaki, employing the local linearization method for stochastic or random differential equation. This method guarantees both fidelity and stability, which allow non-explosive discrete time dynamical system, thus providing discrete time mimicking of the original continuous time dynamic system. This is how the discretization of the model looks like, where synaptic connections and conduction delays are separated as an algebraic restriction, helping to numerical integration. These calculations were done using the MATLAB symbolic toolbox via a live script. The classical neural mass model formulated by Jansen and Reed was modified to take into consideration conduction delays, linking anatomical connections and time delays, making the temporal dimension well represented and the simulations more realistic. We implement a brand new type of realistic conduction delays, and for that we explore three types of delays tensor, given by instantaneous, synchronized, and distributed delay tensors. As an example of what are we doing right now, we are exploring the influence of time delays and connectivities in the thalamocortical system. And in this simulation, we analyze the interaction between neural masses coming from the cortex, the reticular nucleus, and the thalamus. In this example of simulation using our neural mass model, we can observe different differences among delays and connectivity. To illustrate some properties, let's have a closer look to the displayed on the fifth row in the first column. Here we can see clearly changes among the delay, and they are in accordance with their spectrums. For example, in the case of delay 1, we obtain 3 peaks, and we can perceive a slow alpha rhythm, while for delay 9, we have 4 peaks in the spectra, and we obtain a zeta rhythm. We consider that further studies must be done in this area to new phenomenon could be introduced with changes on delays and connectivity. As conclusions, with the new consideration of delay, the temporal dimension was extended, representing the interaction between neurons through the connectivity tensor via specific connection weights and time delays. This tensor efficiently encodes any realistic delays between neuron masses, including distributed delays. Numerical calculations are fast and efficient. We use an algebraic formulation and the local linearization method. The study of the influence of connectivities and delays into neuron mass model is extremely important due to the introduction of new phenomena. And we propose a totally new toolbox for brain modeling that integrates symbolic and numerical analysis to provide a new way of introducing delay into neural mass model. Thanks a lot for your attention.